In this section, let's take a look at the concept of the difference quotient of a function.
Let's begin with the definition. Let's let f of x be a function of x. Then the expression f of x plus h minus f of x over h, where h is any number other than 0, all right, because dividing by 0 would make this undefined, is called the difference quotient of the function f. So let's talk about some interpretations. What's a way we can visualize what this is saying? All right, so let's begin with a graph of some function. It doesn't really matter what that function is because we can define a difference quotient for any function. So here I'm going to start with an arbitrary graph of just some curve. It doesn't really matter what curve it is, so I'll just keep it simple. Something like this. Okay. So there we go. Here's our function f of x. Now, I can plug in any number I like into my function. So here I'm going to plug in I'm going to plug in x, and if I plug in an x, I'll get a y value. Well, yeah, but that y value is the value that I get when I plug x into my function. Okay, so here that's going to be f of x. All right, so here this is the graph of y equals f of x. So if I plug in that x, that's the y I'm going to get. Now, let's say I plugged in another number, different from that x. So let's say I plugged in this one over here. Now, I could call that something else. I could call that, well, I shouldn't call it y because I already have something that's called y, but I could call it x2. I call it w. I call it whatever I like. Well, sure, I can call it whatever I like. But what I'm going to do is I'm going to call it something that relates back to the original number that I plugged in. Say, for example, if this was the number 5, I don't want to think of this as being a totally separate number. I want to think of this as being 5 plus a little something. Well, I don't know what this number is, nor do I know how far these are. So the best I can do is I can say it's x plus a little something. So we're going to use the symbol h, x plus h. So x is the position of this first number, and h is just how far apart these are. That's your h. Okay, so if I plug in x, I get that y value. So if I plug in x plus h, I'm going to get this other y value. Okay, so if I plug in x, I get f of x. If I plug in x plus h, I get f of x plus h. The way functions typically work, whatever you plug in, that becomes the argument of your function. Okay, so now what? Well, think about a curve with relation to a line. Lines are simpler. Lines are easy to deal with because I know everything I ever need to know about any line as long as I know its slope and its y-intercept. Y equals mx plus b. If I have a line, my function is very easy and predictable to work with. If I don't have a line, if I have anything else, well, then it's going to be more complicated to work with. One of the things that's different is that, as I mentioned just a moment ago, if you have a line, it has a slope. A curve doesn't have a slope. Well, no, it doesn't. But I can take 2 points on that curve and define the slope between those. So here, let's pretend that instead of having a curve, I had a straight line that connected both of those points. What's the slope of that line? Well, let's see. The slope of a line, it's the change in the y values minus the change in the x values. This is the slope formula from algebra. y2 minus y1 over x2 minus x1. Okay, so I want the bigger of the y values minus the smaller of the y values. Okay, so that'll be f of x plus h. That's the bigger one. minus f of x, that's a smaller one, over, and then I want the difference of the x values. So here I had f of x plus h minus f of x. So I got to make sure I do it in the same order. I'm going to take the x value that gave me this y value minus the x value that gave me this smaller y value. Okay, so that's going to be x plus h minus x. So that's just the slope of that line. That's the bigger y value minus the smaller y value, and then the corresponding x minus the corresponding x. The bigger one minus the smaller one. Notice here x minus x is 0, so those cancel out. And so you're left with the slope of this line. Incidentally, this is called a secant line. A secant line is simply a line that connects 2 points on a curve. The slope of the secant line is f of x plus h minus f of x over h. Hey, that's the difference quotient. Right? Here, this is the difference quotient, and it is the slope of a line that crosses through 2 points on a curve. It's a way that we can take something that doesn't have a slope and consider a slope between two parts of it. Okay? This is also one of the first elements of defining a derivative. For those of you who go on to take calculus, this will be the first step in defining what's called a derivative. But for now, this is not calculus, it's just some basic algebra. So let's take a look at some examples of how to compute the difference quotient of different functions. Let's begin with something reasonably simple. Let's take a quadratic. So let's find the difference quotient of, let's say f of x equals x squared plus 5x. Okay. All right, so let's go ahead and give this a try. We're going to find f of x plus h first of all. Okay, well, x plus h is what you get when you take your function, instead of plugging in an x, you replace that with an x plus h. So it's going to be x plus h squared plus 5 times x plus h. If we square this, that's going to give us x squared plus 2xh plus h squared. And if we distribute the 5, that'll give us 5x plus 5h. Okay, so now the difference quotient is f of x plus h minus f of x over h. Well, we now know what all those things are. We know what f of x plus h is because we just found it. It's going to be x squared plus 2xh plus h squared plus 5x plus 5h. And from that, we're going to subtract f of x, which was the original function. And then you're going to divide by h. Okay, well, some stuff simplifies here. Notice x squared minus x squared, that's gone. And 5x minus 5x, that's gone. So we're left with something a little simpler. 2xh plus h squared plus 5h over h. And notice that each of these can be divided by h. So let's go and do the division. 2xh divided by h. Well, the h is divided away, and you're left with just 2x. h squared divided by h. Well, those two h's multiply together, divide one away, leaves you just 1h. And 5h divided by h, the h's divide away, and you're left with the 5. So this is our difference quotient. Again, looking at it geometrically, or graphically, what we have is, we have a parabola, something like this. Here, this crosses at the origin, because of course if you plug in 0, 0 plus 0 is 0. Okay, so 0, 0 is part of the curve. And if you plug in negative 5 squared is 25, and then 5 times negative 5 is negative 25, which will also give you 0. So here that's negative 5. Those are my intercepts. Okay, so I have this parabola that looks like that. What this is saying, what this difference quotient is saying is, okay, give me an x value. Oh, let's say negative 4. Okay, so negative 4. Let x equal negative 4. There's nothing special about negative 4. I'm just picking some number for the illustration. Okay? Now, if you plug in negative 4 into your curve, into your function, you're going to get this point. All right, now let's say we're going to move some distance away from negative 4. Oh, how much? Oh, I don't know. Let's say we take half a step away. Which way? Oh, let's go to the right. So we're going to add. So here that's negative 4. And then over here, we're going to take half a step away. So now this would be negative 3.5. So here h is positive 1/2. Okay. All right, well, notice if you plug in negative 4 into your curve, you get a y value. If you plug in negative 3.5 into your curve, you get a y value. Imagine you're connecting those. Hey, that's a line. That line's going to have a slope. What's the slope of that line? Hey, you know your x, you know your h, plug those in. So here the slope of this line is 2 times your x plus your h plus 5. Okay, so that's negative 8. Negative 8 plus 5 is negative 3. Negative 3 plus 1/2 is negative 2.5. Negative 2.5. Hey, that's the slope of that line, negative 2.5. If you had a different x, or if you had not gone half a step away, gone a quarter of a step, or 1 full step, or however many, all this is saying is, okay, if one of your points is here, and the other point is that far away from it, here's that 1/2, the distance between those two. If one of your points is here, and the other one is that far away, connect them, that'll be your slope. That's what geometrically, graphically, that's what that's saying. But even without the graph, we can compute the difference quotient as we see here. Okay. Now, whenever you have a polynomial that you are trying to find the difference quotient of, it usually works out fairly nicely, because all you're going to do is you're going to plug in x plus h, you're going to expand it, and then a bunch of things will cancel. However, if you have something that's not a polynomial, then it will still work out, but it's going to take just a bit more algebra to make it work out. So let's consider for a moment another example. Let's find the difference quotient. Of f of x equals 1 over x, or we can also write this as x to the minus 1. Either of those is fine. All right. So let's go ahead and do that. First of all, we need to find our f of x plus h. Okay, well that's going to be, we're going to replace that x with an x plus h. Okay, so that's x plus h, 1 over x plus h, like that. Okay, so now we're going to have to find f of x plus h minus f of x over h. Okay, well we know what f of x plus h is. It's that thing right there. 1 over x plus h. Minus, well, your f of x was your original 1 over x, and that's over h. Okay, so actually setting up the difference quotient was actually even simpler here than the last one. But now we need to simplify this. Okay, so let's go ahead and combine these terms. Here, these are fractions. And to add or subtract fractions, you need a common denominator. Okay, so let me multiply this by x plus h on the top and bottom. And let me multiply this by x on the top and bottom. So now they have the same denominator, x times x plus h, x times x plus h. So this is x over x plus h minus x plus h over x plus h over h. Okay. All right, well now these have the same denominator, so we can combine in the numerators here. Here, x minus x is 0, that goes away. So this will leave you just your negative h over x plus h over h. Like that. Oh, actually no it won't. I forgot that extra x here, didn't I? So that would be like that. There we go, much better. Yeah, So that's x over x times x plus h minus x plus h over x times x plus h. So here, that's the common denominator. Okay, and now notice this h and that h divide away. So in the end, your difference quotient is, you have a negative 1, after all the h's divide away, you have negative 1 over x times x plus h, or if you prefer, you can distribute that out, and you get negative 1 over x squared plus xh. Just like that. And either of these would be an acceptable result for the difference quotient. All right, so that's not too bad. It's a little bit more than just subtracting. We need to worry about rational expressions by finding common denominators, but that's still not terribly bad. Well, let's take a look at another kind of function. Let's consider now a trigonometric function. Let's find the difference quotient. Of f of x equals the sine of x. Well, let's give that one a try. If f of x equals the sine of x, well, then f of x plus h is simply the sine of x plus h. Okay, well, that looks fairly simple. So now if I find the difference quotient, that's going to be f of x plus h minus f of x over h. And that's going to be the sine of x plus h minus the sine of x over h. Okay. Well, now the hard part is simplifying. Substituting in x plus h in terms of, instead of x was simple enough. Setting up the difference quotient was simple enough. But now, unlike our previous examples, we don't just have things that subtract, nor do we have something as nice as a rational expression that we can just find the common denominator of. But still, we should have some way of simplifying this, no? Well, right here I notice I have the sine of the sum of two expressions. So that means we can use the sum formula for the sine function. Now, right now, what I'm about to do is I'm going to rewrite this. It's not actually going to look any simpler than what this is. And depending on your point of view, it might actually look more complicated. However, this is a meaningful complication. It is a meaningful way of rewriting it. Again, for those of you who go into Cal 1, this is one place where we begin. We pick up where the difference quotient leaves us off. And this way that I'm about to rewrite it is a meaningful thing once we take the difference quotient to the next level in Calculus 1. So here, I'm going to rewrite this as follows. I'm going to say sine of x plus h. Well, by the sum formula for the sine function, that's going to be sine of the first angle times the cosine of the second one plus the cosine of the first angle times the sine of the second one. That's just the sum formula for the sine function, minus the sine of x over h. Now, again, you may notice that nothing really simplifies here. Nothing cancels out. One thing that is now simpler is that we don't have any arguments that have the sum or difference of angles. It's simply sine of something or cosine of something. Right? So in a way that is simpler, but in a way it's also more complicated because now you have another term. Before you only had two, now you have three. Here, we're going to rewrite this one more time. I'm going to notice that sine of x is common to those two terms. So I'm going to write this as sine of x times cosine of h minus 1, like that, after all. If I factor out sine of x from those, I'm left with cosine of h, and then minus 1, and then plus cosine of x sine of h, and all that's divided by h. For now, that's about as far as we can take it. In calculus, we're going to, early on, see that these expressions, cosine of h minus 1 over h, and sine of h over h, can be simplified in a very meaningful way under certain conditions. But for now, without that ability, that's about as far as we can take it. So here, the difference quotient for the sine function would be this, which simplifies to this. Right? I've rewritten it this way which for now isn't really any better or worse than the previous line. However, it will be meaningful once we learn what happens here. And that happens very early in our next course in Cal 1. All right? So for now, the difference quotient would be really either of these would be acceptable for our result. All right, so go ahead and give this a try. Here I was mostly trying to expose you to the trigonometric one, but really the ones we worry about don't involve trig functions just yet because, as mentioned, we don't quite have the ability to simplify that last step. However, we do have the ability to simplify things which are not trigonometric. So go ahead and try the following. Find the difference quotient of f of x equals, let's say, x to the third minus 2x. That should be fine. And then try this one as well. Find the difference quotient of f of x equals the square root of x. Go ahead and give those both a try. Go ahead and pause the video, give yourself the time you need, and once you're done, you can unpause and we'll go through those together. All right, so let's try this first one here. If we take f of x plus h, that's going to be x plus h to the third power minus 2 times x plus h. Here, x plus h to the third power simply means x plus h times x plus h times x plus h. So you can just do these one pair at a time here. Multiply those together. That's going to give you x squared plus 2xh plus h squared. And then take that answer and multiply that by x plus h. And that will give you x to the third plus 3x squared h plus 3xh squared plus h to the third. And if you ask, how did you do that so quickly? This is one that appears fairly often, so I kind of just remember it. But of course, if you don't remember that, you can always just distribute, right? X times x squared, x times 2xh, x times h squared, h times x squared, h times 2xh, and h times h squared. You combine your like terms. Okay? So that's going to give us that expression. X to the third plus 3x squared h plus 3xh squared plus h to the third minus double x plus h. Okay, well, minus double x and minus double h. I just distribute my minus 2. Right. So now, to find the difference quotient, I'm going to take f of x plus h, which I just found, minus f of x, which is what I started with, and divide the whole thing by h. Okay. So here, I'm going to take x cubed plus 3x squared h plus 3xh squared plus h to the third minus 2x minus 2h. That's your f of x plus h that we found in the last step. And now I'm going to subtract away the original function, x to the third minus 2x. And all that gets divided by h. Notice here, x to the third minus itself is 0, and negative 2x minus itself is also 0. So those two go away. And you're left with x to the third. Oh, no, I'm not. You're left with 3x squared h plus 3xh squared plus h to the third minus 2h, and then all of that is being divided by h. So in the end, we can divide each of these by h. Here, that h divides that h, so you're just left with 3x squared plus, here h squared divides by h. That gets rid of one of the h's, leaving you just one more. So that's 3xh plus h to the third divided by h. That leaves you h squared. And minus 2h divided by h. The h's divide away, leaving you your minus 2. And so this is the difference quotient of the function f of x equals x cubed minus 2x. Looking at the next one, we can now take f of x plus h to be the square root of x plus h, like this. All right. So now we are going to, well, that's simple. That was simple enough. We're simply replacing that x with x plus h. But now we're going to set up our difference quotient. We're going to take f of x plus h minus f of x over h. And that's going to equal to square root of x plus h plus the square root of x over h. Oh, my apologies, that should be a minus there, shouldn't it? There we go. It helps if I write things correctly. Minus f of x. All right. So now here, this one doesn't simplify nicely in any way that completely gives you just a polynomial. And nor do we expect it to, since it's a radical. Here what we're going to do is we're going to rationalize our numerator. You'll recognize this, even if you don't recognize the name, in algebra when we try to simplify things with radicals in them. Again, this, like the trigonometric function that we saw a moment ago, is one that simplifies in a way that it does reduce things down because you'll no longer have some expression like this with a division by h, but you will not have something quite as nice as you would expect from a polynomial. In calculus, that simplification can be carried a little bit further, but for now, it's simply a matter of algebraic manipulation. The punchline happens in Cal 1. So here, what we're going to do is we're going to multiply the top and the bottom by the conjugate of the numerator. And that's an expression you may remember from algebra. Whenever you multiply conjugates together, it simplifies radicals, and it simplifies complex numbers as well. We don't have anything complex here, but here we have radicals, sums of and differences of radicals. Okay. All right, so by doing this, what we're going to get is, all right, well, you multiply these two together. That's root x plus h times itself. That's root x plus h squared. And the square will get rid of the root. Okay. If we multiply these together, well, that's just plus root x times root x plus h. Now, if you multiply these together, that's a negative root x times root x plus h. So you'll see those subtract away. And finally, when you multiply these two together, you have a negative times a positive is a negative. And then root x times root x is root x squared. And the square will get rid of the root, leaving you just an x. Here, I could distribute the h, but I'm not going to, for a reason that you'll see here in just a moment. Like this. Notice now that several things divide away, several things subtract away, rather. Those two subtract. Root x times root x plus h minus itself, that's 0. And here, x minus x is also 0. So here you're left with h over h times the square root of x plus h plus the square root of x, like this. And of course here, these h's divide away. And so now we've simplified. Note that it actually does look very similar to what we had before, except now we've gotten rid of one of the terms. Oh, and also this has got a plus in there now. So that's an h over h is 1 over the square root of x plus h plus the square root of x. And that is our simplified difference quotient. Right? So here, yes, it is simplified because, of course, we did get rid of one of our variables. We got rid of an h here. But you may struggle to think, why is this significant, or why is this significantly better than this? Yes, it noticeably is simpler, but why is this the one I want? Again, in the beginning of your Cal 1 course, you'll be able to take the final step to simplify this further. There are certain arrangements of difference quotients that can be simplified down quite nicely. For now, it's sufficient to know the definition of a difference quotient, be able to apply it, even if the simplification is not something that you can do to any particular point, as long as you could say this is equal to this. That is a good start. The one that you should know how to do and simplify as much as possible is one that begins with a polynomial. If you begin with a polynomial, you should be able to not only establish the difference quotient, but also simplify it down to a polynomial in lowest terms. Combine all like terms and have it as simplified as possible. If it begins with something that's not polynomial, like a radical or a trigonometric function, you should at least be able to set up the original difference quotient, even if the simplification isn't quite obvious, or even if the simplification isn't one that you don't carry out, as far as I did. But for now, that's it. That brings us to the end of this topic and the end of our section. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.